G'day guys, we've got a circle geometry question today where we've got a triangle ABC that has a side AB with length 7 centimeters, side AC which is equal to 6 and side BC which is equal to 5. Three circles are drawn, one with centre at A and radius 4 centimeters. So let's write these ones in. So we have radius 4 centimeters of this circle, so this bit here is going to be 4 and so is that. One with centre B and radius 3. So there we are. And one with centre C and radius 2. Great. So, what percentage of the triangle fails to lie within any of the three circles? Okay. So basically what the question is asking us to do is it's asking us what percentage is this part of the triangle. So that's what we're going to have to solve. Now, when we're going through this question, the way that I went about solving this is I rewrote the cosine rule in terms of the angles and used the cosine rule to determine two of the angles and then subtracted it away from pi or from 180 degrees. So let me go through what I did with the cosine rule to start with before we even get into the question. Okay, so hopefully you guys are aware that the cosine rule is equal to, or we have like c squared, the side, is equal to a squared plus b squared minus 2ab cosine c. Cool. So with this equation, what we can actually do is we can rearrange it so we have the angle, let's just write so you remember there's the angle C, is equal to the inverse of cos times a squared plus b squared minus c squared all divided by 2ab. Cool, so here is our cosine rule when we're looking for a side, and here is our cosine rule where we're looking for an angle. Alright, so let's get to it. To start with, what I'm going to do is I'm just going to pick a random angle and I'm going to try and find that. So let's go for this one here, angle at vertex A. Alright, so what we're going to do is we're going to go, well, this is equal to the angle at A is equal to the cosine of -1 of a squared plus b squared. So the side's next to it, so we're going to have 7 squared plus 6 squared, because this side here is 7 and this side here is 6, minus the opposite side, 5 squared, all divided by 2 times 7 times 6. Great. And we just put that straight into our calculators. And to be perfectly honest, with a question like this, you probably would like to do this in radians, just for the second half of the question. So this is going to equal 0.775 radians. Okay, so that's this one here. So we've done that one. Now, let's have a go at angle C. So we have this one here, the largest angle of the triangle, the one that's opposite the longest side. So let's do that one. Angle C is going to be equal to the inverse of cosine in brackets. The two sides adjacent to the angle. So we have 6 and 5 added together. So 5 squared plus 6 squared minus the opposite side, 7 squared, divided by 2 times 6 times 5. And if we put that into our calculator, we get 1.369 radians. Okie dokie. Now, to work out the areas of the sort of the pizza slices within each of the circles, we're going to need the angles of each of the circles. So if you're wondering why I'm going about getting all of the angles, that's why. So the last one we have to do is B. Now, rather than putting it into this laborious cosine rule, we know that the interior angles of a Euclidean triangle is equal to 180. So what we're going to do is we're going to just subtract this from pi. So we're going to say angle B is equal to pi, subtract 1.369, subtract 0.775. And that is going to be equal to 0.998 radians. Cool, so we have our 3 angles now. Great. So, now what we're going to have to do is to work out the percentage of the triangle's area. We're going to have to work out what the total area of the triangle is to start with. So let's do this over here. We'll make a sort of a digression. So over here we're going to have the area of the triangle, and we're going to use, because it's not right angled, we're going to use this one. The area of a triangle is equal to half AB sine of C, which is equal to 1/2. You can use any of the sides with any of the angles. Let's just use this one here. So we're going to have A and B being 5 and 6. And 6, and sine of C, which is 1.369. Sine of 1. And that gives us the total area of the triangle of 14.694. And that's in centimeters squared. Cool. Now we have to find the total area which is contained within each of the pizza slices. So that, added to that, added to that. So let's go about doing that piece. So what we're going to do is we're going to have the area of the circles. We're going to use the formula, the area of a sector is equal to 1/2 r squared theta. And I'm just going to put all of these into one big long summation. So we're going to have the area is equal to half the radius of the first one, 4, squared, times the angle of A, 0.775, plus half of B, 3 squared, times 0.998 plus half of 2 squared times 1.369. And if we just put that straight into our calculator, we get an area of 13.429. Cool. So once we've done that, it's pretty self-explanatory that what you're going to do to find the gold piece in the center, you're going to get the total area of the triangle and subtract away the area contained within each of the, contained within the total of the circles. So what we're going to do, let's do this bit in gold because we know, so it's for this piece. So the area is going to be equal to 14.694 subtract 13.429, and that's equal to 1.265. Cool. So like the question says, this is the area of the triangle that fails to lie within any of the three circles. All right, but it's asking us in the question the percentage. So finally, let's do this percentage. So the percentage of the area of the triangle. So it's going to be 1.265 divided by the total area of the triangle times 100/1. And that, my friends, is going to give us a percentage of 0.00. Cool. So that's us done for this question. We've solved what they've asked us to solve. And yeah, I think we've set it out pretty well. So let's just go through what we've done. Now, the easiest, fastest way to solve this question is, because we have all of the side lengths, we can rearrange the cosine rule. So we get this one here. So this one here is for a angle rather than a side. And what we do is we use this to work out two of the three angles of our triangle. Then what we can do is we can use the fact that the interior angles of a triangle add up to 180 degrees to find the third angle. The reason we had to find all three is because when we're trying to find the areas contained within the circle and the triangle, we needed the angles for each of the vertices of the triangle, so we could get each of their associated circle areas. Once we'd done that, we just summated all the circle areas which are also contained in the triangle, and then banged our answer out with that. So if these are the circle area which is in the triangle, this is the triangle area. The circle bits that aren't in the triangle, the bits that aren't in the circle which are also in the triangle, is going to be the difference. So we subtracted one from the other, and we got this 1.265. We then divided that by the total triangle area to get our percentage. So it's a relatively complicated question, guys, but you know, if you understand how to manipulate all of your formulas for angles and segments, sectors, and arc lengths, and all these kind of things, as well as obviously, hopefully you guys are already aware of how to work a percentage out before you come to a video like this. But once you've got these formulas under control and knowing how to sort of rearrange them so you can get the variable or the information that you're after, then a question like this shouldn't take too long and shouldn't require too much brain power. But again, I hope this video helped, guys. If it did, give it a thumbs up. I make new videos all the time about, maths and science and stuff like that. If you have any problems with your maths or physics or chemistry or whatever, send us a question. I'm always looking for new ones, and I'll be happy to give it my, the old college try. But until next time, guys, have a good one.